This is John Black, super chemist. Someone asked me to do this video, so I'm going to do it. Now, there's two things that I couldn't understand. I never really got into this part of physics, so I'm going to have to, because I need to know about light and how building atoms. But it took me a while to understand why it was catastrophe like, or why the whole thing is, my whole answer to everyone is, oh well, they just said, someone said it was quantized energy, and that just solved everything. What does that mean? Yeah, so we'll get into that. First of all, I want you to understand, everybody emits light. Everybody emits light, right? Every object, everything in the universe, okay? If you're not emitting light, that means you're at absolute zero, and that cannot happen, okay? It's not possible, all right? So everything, you, me, this lighter, everything is emitting light, okay? You're emitting it from all different colors and all different ranges of light, you know what I mean? Obviously, it's all good light. It's not, it's not like you're radiating gamma rays or something. But you do put, have a big continuous spectrum of light color and light wavelengths that you put off. And you can see it if you have the right equipment, you know what I mean? But as your human eye, you're not going to see it, you know what I mean? Sometimes you can on some organisms and things, phosphor in the dark or whatever. But you don't see this, okay? So what's the catastrophe? Okay, basically, I'm going to tell you the two catastrophes and then tell you a little bit more. The two catastrophes are this, okay? They had, this guy Boltzmann, see how it has a K with a subscript there, B? That B is for Boltzmann. That's his constant, okay? And he figured everything out, What it is when you heat something, right? You see these colors, right? You heat something, the hotter you heat it, the more, the wavelength changes. It gets shorter and shorter, more and more energy, right? It starts out glowing red and orange, yellow, green, and obviously it's putting off all kinds of colors. So you might not be like, oh, wow, that's really green, because it'll blend in, then blue and purple and so on. So Boltzmann, right? This is the whole deal when it comes to like any science, okay? First of all, you find something out, right? Then you, like about this light, you know what I mean? Oh, you heat something up and all these photons get thrown out, you know what I mean? It glows. You make up, you start doing ginchy little experiments, right? You try and make a formula for it, to describe what's going on, right? To do the math, right? So that's what Boltzmann did, right? Here's his equation. Is it perfect? No. Does it work? Yeah. People use this equation today. They're going to, 100 years from now, 500 years from now, they're going to be using this equation. I guarantee you, okay? It works perfectly fine when it's low, when you're not trying to heat it up to like the temperature of the sun, okay? And this graph right here, over here, the vertical axis is the like the light intensity, right? The x-axis going back and forth, the horizontal, that's your wavelengths, right? So if here's like low energy, like infrared and lower, and above these colors here, see, that'd be like UV and even more shorter wavelengths, so they're more energy. And you can see in between you got the colors, if you know the light spectrum, you know what I mean. And basically what they did was they heat something up, right? And they'd see how, and they keep heating it up, and you'd see that it would move over this way, you know what I mean? It would go from infrared up to, because you're doing all kinds of photons, but mostly there's a peak at each time, you know what I mean? Each temperature. And, the average, most of them would be like where, where the hump is, right? So anyways, they did experiments. As long as they got them, like, I don't know, I'm making up numbers here, about 5,000 degrees or something like that. Everything worked out perfectly fine, okay, with their equations, what, happened, what wavelength was coming out or whatever, his thing was perfect. And it still is today. but it only worked for lower temperature. When you went to extremes, the equations didn't work. Experimental things was saying that it was more like this, and his equations is more like this, where you just keep hitting, it stands to reason if you heat something and it gets red, and then it gets orange, and then it gets yellow, and then it keeps going all the way up and up. It's, anyone would assume, well, if you keep heating it more and more and more, the energy is going to be more frequency, more energy, and you'll go up to UV until you're just like, gamma rays are we can humming out and stuff. Okay, and that doesn't happen, right? So instead of just saying, oh, see, this happens every time. They have a formula, they whatever. Doesn't mean that this is wrong. It is wrong, but it doesn't mean it's just garbage and all classical physics is just BS because this is how science works. You find something out, you do some experiments, you have an equation, right? And then you make more and more. See, the thing is then you make more and more experiments. The first experiments aren't freaky and whatever. They're just trying to figure stuff out. But then when they figure it out and they got an equation, now they want to see if the equation works. So then they start doing more weird stuff with the experiment. And in this case, they have the temperature go higher and higher and higher, right? And it wasn't the experimental evidence was saying that this equation was wrong. That's the ultraviolet catastrophe. Why? Because it happens around at the UV range, you know what I mean? You're getting hotter and hotter and hotter. At UV, it's hard to get it higher than that, you know what I'm saying? So that's all it is. It's just that the experimental evidence didn't back up his equations only when you went really high and extreme, you know what I mean? So a second reason, right, is this one, the black body thing, right? Black body just means that it's insulated and it just has a little hole there, right? And it has little light absorbing stuff inside there, you know what I mean, like black and that kind of thing. And the hole is really tiny. A black body is something that what happens is you get light thrown on you, right? When you absorb it, right, the electron jumps up to it has more energy now. You got energy from that photon, right? So it jumps up, but then you're not giving it any more energy, right? You only gave him a photon, right? So he can only stay up there for, and then he drops back down because he don't have the energy to be in that upper energy state, right? So when he falls back down, the electron throws back an equal, the same exact type of photon that it got, right? And it throws it off, and this black body, right, would be something that kept all the photons and didn't throw any of them back. You know what I mean? And that's impossible to have. So they just keep in mind, the box inside the box inside, that's not the black body, okay? The black body is literally the hole, the area that doesn't exist, right? That, because when photons go in, they bounce around, they get absorbed by the black surfaces, and they don't really come out as much because there's a tiny hole and that's the only way out, and everything gets absorbed because it's so black. So because of a thought experiment, right, they say, oh, you get this black body, it's not giving out, as much of the photons as it's taking, right? You're going to have all these photons being stuck in here. Because even though they get absorbed by the black body, right, the walls and the sides, those are going to, even in total darkness, photons are being thrown in your face and your eyes. I don't care how dark it is. Photons are being thrown at you, okay? It's just there's so little when it's dark, you turn out the lights, you can't, and plus a lot of it is infrared, right? It's below where you can see it, okay? But anyway, so now you have this black body. In theory, on paper, because of this formula here that doesn't work for higher temperatures, right? This thought experiment, right, is saying that since it's absorbing all these photons and it doesn't let any out, right, that these photons, as they go back and forth, right, they can get any, they're going to oscillate, right, but they can have any, that they should be able to form any type of standing wave, you know what I mean, as they're getting tossed back and forth or whatever, right? So that I don't understand how they would think that, since they're telling us, right, that when they collect a photon, they can only throw out a photon at the same exact energy. So I don't even know how they. Well, this was before they figured that out, I guess. Okay. So the thought experiment is they can be standing waves in there, right? And sooner or later they can get smaller and smaller. They can get bigger and bigger. It's just all about probabilities. You know what I mean? There's always going to be a little bit go this way and a little bit go that way. Most will go this way. That's why they call it a wave function, because it's just a probability that, you know what I mean. So anyway, the thing is, if you can do that, it's like a pot of water that's boiling, right? It's 90 degrees or 200 degrees, right? And it's boiling, coming up to a boil. And not all those molecules in there are the same temperature. Most of them are close to that 200 and whatever degrees, right? But some of them are a little bit above it, a little bit even more above it, and some are a little below, even a little lower than that. You know what I mean? There's even one that's really freakishly, slow. You know what I mean? Because it's all about probabilities. Okay. So the probabilities is that if that's true, then one of these, at least, or some of them, at given time, will divide up and be more and more frequency. You know what I mean? More and more energy, until this box has so much energy in it, right, that it just explodes or whatever, and the whole universe goes away. It is a thought experiment. So now they're all confused, right? What is going on here? Why doesn't this work? Well, it doesn't work because it's the first formula they made, man. What do you expect it to do? Work on everything, you morons? That isn't the way it works. It never works that way. Why would you think it would work that way? He had a great thing that works still today, and we needed to get better, you know what I mean? But to say that this is crazy and this is crap and classical physics is just stupid. Why? Because the first thing, these people, keep in mind, I'm reading a book right now, right? And this guy, it's a paper that he did from J.J. Thompson. It's online, you can get it. Did a paper called Cathode Rays. He, or else maybe it was Planck I was reading about it. I don't know, one of them. He's telling me about how he's doing an experiment, right? And he's, shining light out, and he's trying to, see why the colors don't, like he's trying to say, why doesn't, yellow light and green light make blue light? You know what I mean? He's confused and he's whatever, but the experiment is so stupid. I mean, back then they didn't know anything though. Today, of course, it's stupid. But keep in mind, this is back then. This is like 1905 or something. These people don't even know what an electron is. I'm reading a book from 1905. They're calling them corpuscles. That's what they called electrons, because they weren't sure if they were what they were. So that's at the point where they're at. You know what I mean? So, and I watched a couple of videos to do this video just to see, if I could see something extra that seemed interesting. And they all seem to think that Planck came up with quantized energy. Planck didn't come up with that. Bohr had that before him, and J.J. Thompson had it even before him. So I don't even know what the heck, but anyways, somebody suggested quantized energy, right? And we've all heard of the Bohr model, right? You got these little levels, right? You got electrons in there, and the photon comes, hits the electron jumps up to another level, right? But he can't stay there, so he jumps back down, and as he does, since it's the same amount of energy, right, to get up to come down, he throws out the same exact energy, photon, the same thing. Now this is the thing, it took me a long time to get over this, or to understand, because that's all they always tell you, right? Because I got into physics, not this part of it though. I just read, I know a little bit, but I don't know, the whole thing. I never really was interested about this part. But I never understood, because it never seemed to explain, who cares? I mean, yeah, I care that he said quantized energy and the levels and all this BS, right? I mean, it's not BS, but all this stuff here, you know what I mean? I get it, it's great, blah, blah, blah. How does that fix this problem. It doesn't have anything. It doesn't.